Hey, Paquito.
Hi,
How you doing?
Miguel.
What's up? What's all this about?
Just drawing.
Yeah, they're good. Especially this one. Looks like me.
I know.
Where are you supposed to be?
ETs.
What?
Extraterrestrials.
But they can't be.
Why not?
Because extraterrestrials don't look like this.
How do you know?
Because they just don't. I mean, look, you got them all looking like humans.
Well, they might. You never know.
Now, Paco, the only reason why humans look the way they do is because of Earth's atmosphere and gravity and stuff like that. Now, unless a planet has exactly the same conditions, things are going to be different.
Different? How?
If the Earth were different, say if it were as big as Neptune,
How big is Neptune?
15 times bigger than the Earth. Maybe. Anyway, a lot bigger. If the Earth were that big, you'd be really short.
I am short.
I mean, you'd be really short. And squatty.
Squatty?
Very squatty.
Great. Why?
Because the pull of gravity would be a lot greater. And it pulls you down harder. It would be harder to lift stuff, and it'd be much harder to move around. You'd probably have to crawl everywhere.
Could we try a different planet, please?
Well, how about the moon? If the Earth were much smaller, say the size of the moon, you'd be taller.
Taller is good. How much taller?
Pretty tall. And very skinny. And you'd probably be jumping around a lot.
Why?
Because you'd be so light. Everything would be lighter. The moon's gravity's only 1/6 of the Earth's.
You know, Miguel, I sort of like things the way they are.
Say no more. But there are a few places here on Earth where life looks a little weird. Like underwater. Most life on Earth depends on oxygen and sunlight, and has to stay within a narrow range of temperature and pressure. But underwater, deep underwater, conditions for life are different. At the bottom of the ocean, under extreme pressure, and in total darkness, we can find life systems very different from ours. Life that depends on the sulfur from volcanic vents. The tube worm.
Looks like a plant.
I know, but it's an animal. A 6-foot-long animal, able to live in an environment totally unlike our own. We can't even go there unless we bring our own oxygen in a pressurized, self-contained submarine. Unlike the tube worm, we have to breathe air. Breathing is essential to human life. In places where there isn't any air, like underwater, we have to carry our own. In space, we need to wear a spacesuit. At the Johnson Space Center in Houston, I got to try on a spacesuit. It took 2 suit technicians, Gene Alexander and Carolyn Johnson, to help me get into it. It wasn't easy.
Okay, doing good. Stand up, right there.
I'm here.
The suit has its own cooling system, cold water tubing sewn into the underwear. And believe me, it works.
Oh, that's
Does that feel
cool.
good?
Yes, it does. What about if it gets too cold?
If it gets too cold, then this is what this is for. This is full cold here, and you turn this around to whatever makes you feel good.
Every piece of the suit is measured so it all fits together perfectly. It has to. If there was even a tiny little leak, you'd die.
Watch your nose. Okay.
In space, there's no air and no pressure. The suit delivers pressurized oxygen. It can make your ears pop until you can get used to it.
The helmet's on now. You have a series of sunshades that will help you should you be subjected to a lot of light. There's one on this side, a gold visor. You have one in the center. And then you have a visor on each side to help block out light should you need it.
This is great. I feel like Darth Vader.
Okay, can you reach those? Right up here? Yeah, right here. Great.
Whoa!
On Earth, the suit weighs almost 200 pounds, so it's tough trying to move around. In space, it doesn't weigh anything. Human beings can only live in a narrow range of conditions. A spacesuit recreates those conditions and lets you carry them with you, just like a little spaceship.
I was working as a research engineer at the Utah Water Research Lab, and one of the other engineers went down to the post office in Logan, Utah, and he saw an announcement from NASA saying they were trying to hire scientists and engineers to go work in space. And it was right next to the 10 most wanted criminals in the post office. Anyway, he picked up a flyer and brought it back up to the lab, and he said, "You're the only engineer working here who's crazy enough to want to do this." And I said, "You're right." It was the first time I'd ever read a job description in my whole life where it all clicked. It was just perfect. I wanted to do every part of it. And it's worked out being that way, too.
Mary Cleve is an astronaut.
I enjoy my work. I think my work is a lot of fun. I think a job should be fun or it's not worth doing. I was born in Southampton, New York, and I was a funny kind of kid, I guess. I spent a large part of my younger years hiding in my room. And then when I got to high school, I found out I could hide in the gym instead, so I hid in the gym and I played on a lot of teams. I come from 3 generations of sort of naturalist type people that are interested in birds and plants and that kind of stuff. I can remember running around when I was a little kid with my great-grandma Clancy, you know, in a garden. And I think that just sort of generalized into an interest in science. I was never a super-duper outstanding student. I'm a strong, always was a strong sort of A- type, I guess. Since I'm an environmental engineer, science means working on the environment. And I'm interested in birds and plants and cleaning up the planet so they will be able to be maintained. My 2 sisters went through adolescence and they were horse crazy. They rode horses and I had horses and stuff. And for me, that craziness was airplanes instead of horses. And so I started flying when I was 14. My first solo flight was great, you know, because I've been flying a lot, and it was fun finally to get the airplane all to myself. And I wasn't really all by myself, though. I had a pet chipmunk. I snuck him on a plane. He lived in my pocket. Come on. I never used to like math. I come from a family that has generations of math anxiety. And I ended up deciding that I wanted to fight my way through calculus, which I literally did. And then it's a lot of fun once you get to differential equations, because math is a language that you speak to anything that can't speak. It's like, if you have a river and it's in trouble and it's trying to tell you what to do to fix it, it does that with numbers. You model it. And so you use the numbers to interpret or talk to the planet. I don't think of myself as an intelligent person. I'm a plugger. A lot of times things don't come really easily, and I have to work at them. When I was an undergraduate student, I attempted to change professions. You know, I wanted to be in aviation, so I applied as an airline stewardess. And I was really crushed. I was 2 inches too short to be an airline stewardess. You used to have to be 5'4" instead of 5'2". So that killed that, so I was back in science again. Working in the astronaut office is, it's a lot of fun, because there's variety. Every day it's different. And we're simulating missions. They write a script just like it's a play, and they make everything go wrong. And you just play through it, and you have to solve all the problems. Periodically, I do get afraid, and I think most people do, but it's just that it doesn't bother you quite so much. Or, in another sense, it's almost exhilarating. There's one thing I want to accomplish while I'm an astronaut, and it has been my primary goal in every job I've ever had, and that's to enjoy myself.
What you doing?
Keeping an eye out for extraterrestrials.
You see any?
Not yet. Miguel, if extraterrestrials don't look like us, what do they look like?
Well, nobody knows, really. It could look like anything. We probably wouldn't even know what it was if we saw one.
You mean like this rock? This rock could be an extraterrestrial?
Maybe.
How would it communicate? Rock signals?
You see, we don't know. It could be some other form of communication we don't even know about.
Hello? Hello, rock? Do you read me? This is Paco.
Getting anything?
It's for you. How would you communicate with an extraterrestrial?
By charade.
I'd probably try and call him on the radio and try to get his frequency, and if I couldn't, then try some sign language maybe.
Maybe touch him or point at something and it might work.
I wouldn't communicate in English, just signs.
How would you communicate with an ET?
With brain waves.
Brainwaves?
Hi, E.T.
Send a telegram?
Probably just talk to him, see if he talks back.
How would you communicate with an extraterrestrial?
Oh, I would probably try to use universal sign language. Provided the guy has eyes and ears as we, I would probably try something to say left, right, up, down.
I'd probably use mathematics.
Mathematics?
Yeah.
If they're truly superior beings, maybe I could think my way into his mind.
I'd probably do it with a ham sandwich.
If I can't do it with my mouth, I will have to do it by my hand or some way.
How would you communicate with an ET? Anzai, o, la.
Beep, 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 beep.
If someone from outer space, like an ET, ever wanted to contact us on Earth, we would probably get the message here. This radar station in Arecibo, Puerto Rico is so large and sensitive that it's like a giant ear on the surface of the Earth. It receives information through electromagnetic waves that come from all over the universe. Jerry Giles has worked at Arecibo for many years, and he showed me around. How would you actually communicate with something from outer space, let's say like an ET?
We'd have to use a very universal language, something that could be understood no matter where you were in the universe, no matter what kind of being you were. But basic to all of these civilizations will be mathematics. And so the most simplest form of mathematics is what we call the binary system, the same kind of counting system that computers use. And it's simple. You only use 2 digits, a 1 and something else, like a 0. And with those, you can communicate very simply, very efficiently, and for long distances.
Signals come in all the time, but not from ETs. All planets and stars give off natural signals. At Arecibo, they are collected in a curved dish that is bigger than 3 football fields. And they tell us more and more about what's out there in the universe.
When we're just receiving very, very, very weak signals, that are produced with stars or galaxies or objects that are far away. The farthest that we can receive from is about 15 billion light years away. That's approximately 24 trillion miles.
That's incredible.
This universe is huge.
I can imagine.
Really huge.
It's just like a wave. That's what you're receiving?
That's what we're receiving right now, right this instant. Now, once it's captured here, it'll be sent through the different receiver parts back to the computer, and the computer will then process it digitally. And then we'll get a picture that looks like this. Now this is a picture of a galaxy.
Just looks like a bunch of wavy lines.
This is very characteristic of a galaxy. It has like two horns here. This tells us how far away the galaxy is from us, how fast it's spinning, how much hydrogen, how many stars are in that galaxy actually.
But did we ever contact anyone out there? Several years ago, some scientists gave it a try, using that 2-digit code Jerry talked about before.
The Arecibo message of 1974 was a demonstration to show how easy it is to communicate using radio waves instead of sending out a rocket or a spaceship or something like that. Within 5 hours after it was sent, it was already past Pluto. And this message, when it left Earth, looked like this.
It's a bunch of ones and zeros.
Right, it looks like, doesn't make any sense at all.
No, it doesn't.
But a group of scientists could get together and analyze these signals, and they would come up with a picture. And this is the Arecibo message. This was sent to a group of stars called M13, which is about 25,000 light years away from us. That means it's going to take 25,000 years for that message to get there. It's a long ways. It's a long wait. Up here is a lesson to tell the receivers how to count using this message. The 5 most important chemicals for life here on Earth. Most of these are chemical formulas, and then we have a DNA double helix, which is important for life here also. The population of the Earth here, that number, this is a number representing about 4 billion people on this planet. Here's the height of the human being, average. Here's our solar system, and of course here is the giant radio dish here in Puerto Rico. All that in 1,679 bits of information.
How long is the message?
3 minutes. Took 3 minutes, that's all. Wow.
So it's going to take 25,000 years for that message to get to where it's going, just to last 3 minutes?
Yeah, right.
Wow.
And then, of course, if whoever receives it sends an answer back, it's going to take 25,000 more years for the message to get back here.
That's a total of 50,000 years we'd have to wait to see if there was any result.
Right.
Well, I don't think I can wait that long to talk to an ET. If there is life out there, it may see Earth differently than we do. These are pictures of Earth as we see it from space.
Now we're in the Hawaiian Islands. That's the junction of the Congo and the Ubangi River in Zaire.
Dick Underwood is a picture expert. He can identify almost any part of the Earth from photographs taken in space. These are pictures that Sally Ride took when she was up in the space shuttle.
Well, we can look at some where the things we never even knew existed before until the space photography came along. And if you look at this picture close, you can see long, thin lines. There's a series of them here, and a series of them here, and another one out here. And these are called internal waves, mainly because usually when you see waves, they're on the surface of the sea. But these are deep beneath the sea, and they only deflect the surface a little bit.
But if they're deep beneath the sea, how did they get a picture of it?
Well, we trained the astronauts after we first saw them about 9 years ago to look where we have the reflection of the sun off the sea in a certain position. And there, with just a small deformity in the surface of the sea, these things will stand out because of the reflection off the sea. So we see the waves. They are moving underneath the sea, and they're a tremendous force. And so that's one reason why we take all these photographs, is so we can better understand this little planet and the people that live on it and their problems and some of the good things about it. Well, here's a neat little thing you might want to look at. Now, if you look up here in Siberia, you can see this big lake called Lake Baikal, and it's the deepest lake in the world. Now, this island you see here on Lake Baikal used to be flat against the land. It was the shore. And during historic times, several centuries ago, from the pressure of the continents colliding here and these plates moving, it broke loose, and it moved out here about 4 or 5 miles out into the lake, and then it stretched, and right in here, if you put the glass on there, you see it stretches just like taffy in a candy store where it's been pulled apart. So we have photos of it.
But this looks like a puzzle piece. Like you can
Right,
just fit it
right,
back in together.
right. It's been pulled apart. And the puzzle would fit together. That's the way it used to be. It used to fit together 200 or 300 years ago, and now it's pulled apart. And we've got a good photograph of that.
Now, does this take place anyplace else in the world?
Well, these continental plates are moving all the time and at various speeds. South America moves at 3 inches a year. Africa pulls away from Asia. California and this area is sliding north, where, a few million years from now, Los Angeles will be north of San Francisco. So we live on an active planet, and these photos tell us a great deal about what's going on. Hello, Sally. How are you?
Pretty good. How are you?
Okay.
Sally Ride is the astronaut who took these pictures from the space shuttle.
You took here.
How do they look?
She asked.
They look great.
She asked a lot of questions on why you took them and their importance and how people around the world are putting them to work today.
Sally, how did you know what pictures to take? Did you take them just because they were pretty or because he told you what to look for?
Some of them we took just because they were pretty. Some of them we took because Dick had told us that he wanted pictures of that or to look for it. The faults, for example, pictures over the islands. We knew that we wanted pictures of islands and island wakes from what Dick had told us, but some of them we took just because we didn't understand what we were seeing. Here's one that I remember taking because it was a cloud formation that I didn't understand. You can see all the clouds right around here, and then there's a ring of them that's a little bit thicker and no clouds over that. And
does that mean the air was pushing against it or something? What is that?
It means probably that there was an upwelling of water of a different temperature from beneath the sea coming up, and the ring is the interface between 2 different temperatures of water. So it's either an upwelling of warm water or cold water. In this case, warm water.
You know, Robin, although we're looking at pictures of the Earth, I'm really an astrophysicist. I'm used to looking out at the sky, out at the stars. But the things that Dick taught us, looking back at the Earth and taking pictures of things on the Earth, really made me realize that we're part of the universe. We're part of the solar system. You can see that by looking at one of these pictures here of an impact crater, something that was made by a meteorite impacting the Earth. You know, when you look at the moon, you see craters covering the surface. And for a long time, people thought that they were only hitting the moon. And Mars has craters that are kind of pockmarked the surface. But it's really, once we got up into orbit, was the first time that we started to realize that there were a lot of craters on the Earth, too. We're hit by the same things. It's just that they're not quite as obvious to us.
And this is one right here?
Right there. You can see the hole left by the crater.
Why aren't they as obvious on the Earth? I mean, how come you can't see them as well as you can on other planets?
It's mostly because of the conditions on the Earth. We've got an atmosphere, so some of them burn up on the way in, so there aren't as many craters as there are on the moon, for example. Also, we've got an atmosphere, so we've got wind and rain and a lot of erosion that tends to hide the really striking bowl-like features.
So maybe sometimes water will fall down.
They might be filled up with water, might look like a lake to us, and we don't think of it as an impact crater.
That?
Moldy bread.
Yuck. What are you going to do with it?
I was thinking of sending it into space.
Why?
Well, you see the mold?
Yeah.
It's living, right?
Yeah.
Even though it looks like weird green junk, it's living.
Yeah.
So I was thinking, since human beings can't live in space because there's the wrong atmosphere and pressure and temperature and stuff, well, maybe the mold could live in space.
Well, you don't...
And because you said that the E.T. doesn't look like us,
Yeah.
this mold doesn't look like us either. Maybe the E.T. looks like the mold.
Yeah, but...
Maybe they get along. Maybe
but-
they'd like each other. Maybe the E.T. and the mold would become friends. This is a friendly mold.
I know.
I know you don't like the mold.
But mold's all right.
But maybe the EC would like the mold. You never know. The Bloodhound Gang will return next week with another mystery.
"321 Contact" is a production of the Children's Television Workshop. For a 321 Contact Teacher's Guide,